Good morning. We are Team National, and we're here to present to you our smart bike powered by Wind River Systems, as well as in partnership with Bolt Motorbikes. Hello, my name is Jacob, and I'm a part of the soccer team, which includes Jim, Camille, Raphael, Christian, and Arden.
I'm Anthony. I'm part of the hardware team, and my team includes Aaron, Dan, Calvin, Erwin, Brandon, and Sergio, and that's it.
So we'll talk about our first sponsor, which is Wind River. They are a software company based here in San Diego, as well as the Bay Area. And their main focus is to create software for data monitoring and data acquisition.
Our second sponsor is Bolt Motorbikes. They're a San Francisco-based e-bike company. They aim to provide an electric bike that's both robust in function and as well as in design. And we come in to make it smart.
Yeah, so their flagship bike is the Bolt M1, and it's a full electric bike. And what we plan to do with it is to combine both the technology of Wind River as well as the mechanics of both motorbikes. And so the features that we'll be adding include a sensor data acquisition as well as a smart battery. We will be able to remotely access the bike via the smartphone, as well as be able to connect the bike to the cloud.
So for the project, we had a couple of goals in mind. One for the user is to make an improved user interface by having an Android-enabled smartphone app, the safety and monitoring with our sensors, and by connecting the bike to the cloud, we enable predictive maintenance by tracking all the data points, and the user will be able to see later.
So in terms of the business side, since we can track all the data, the companies can use this data for research and development, and also potentially have new revenue streams. So people can place charging stations in really high dense areas. And also with ride sharing services, since companies can track and maintain their bikes, it's easy to track all the bikes.
So some may ask, what is dashboard? This image is a good representation of what we worked on throughout this semester. As you can tell, as a summary of what this does, we grab wired data into the Edison, to the phone, to the cloud. And as you can tell, the Edison is the centerpiece of our project, which Erwin will elaborate on.
Okay, so when we were looking at how we were going to monitor information from our sensors, we came across the Intel Edison and the Intel Galileo. These are mini computers that can be used for embedded systems and interface with peripherals. Ultimately, we chose the Edison due to its low power consumption, number of pins available, compact size, and integrated Bluetooth and Wi-Fi. This made a very practical device for application due to our desire to store and compartment underneath the seat of the bike, as well as our objective of communicating information pulled from the sensors to a smartphone using Bluetooth. Taking a look at the specs, Edison has 40 HDMI pins. Some pins we use include the UART and I2C pins. These are used to communicate between the Edison and the microcontroller to relay information from the sensors. The Edison also has a Bluetooth adapter, which is used to communicate between the Edison and the smartphone to show information to the user. For the operating system, we mounted a Yocto Linux image using an Edison breakout board. We were then able to use programming languages such as C++, Python, and JavaScript to code for communication and data monitoring between the Edison and the sensors.
So the first of our subsystems is the load cell. Currently, right now on the bike, there is no weight detection feature. So we are using the load cell for weight detection, which can be used for safety purposes. We don't want the bike to be able to move, or at least the electric motor. We don't want that to move if there's no weight on the seat. We can also use that for calculating the ride distance for a given weight and the current charge of the battery. So what is a load cell? A load cell is a strain gauge. It's a variable resistance with applied force. As you can see on the right, the voltage is changing as I apply more force to the strain gauge. We are using this sensor under the seat to measure the weight, and it'll be communicating to the master Edison, which Erwin talked about, via I2C. And this is a schematic representation of the amplifying circuit for the strain gauge. As you can see right here in the Wheatstone configuration, it's feeding into an op amp, which then feeds that data to a PIC24 microcontroller, and that'll be relayed to the Edison.
The battery is a very important part of our system. It powers all the other subsystems in the bike, and therefore it is very important that we take good care of it. The battery is made up of lithium-ion cells, which can be easily damaged by either going over voltage or under voltage. Because we cannot go over voltage or under voltage, and cells may charge or discharge unequally, they can become out of balance, and therefore when we charge, we can only charge till the highest cell reaches the maximum voltage, leaving some cells not fully charged, and discharge to where the lowest cell reaches the minimum voltage, leaving charge left in the rest of the batteries that we would like to be able to use. To address these problems, we added cell monitoring. We read each individual cell voltage into a multiplexer, looking at one cell at a time, then take that value into the analog to digital converter and send that value to the Intel Edison over an I2C connection. We then also added cell balancing. We do this by connecting a switch and a resistor in parallel with each cell. That way, during charging, when a cell reaches the maximum voltage, we can turn on the switch and discharge that cell back in line with the rest of the cells, then continue charging and bringing up all the cells, discharging the highest cells again, and bringing them all up until they reach the maximally fully charged voltage.
So, as we all know, Bluetooth is a major component that we use to send information back and forth between the Edison. So, we use that protocol to actually create a server socket between them, and we simply send string from one or the other to use it as a remote host or grabbing sensor data. We first do this by setting the Edison as a discoverable. Once we do that, we simply connect to it on the phone. Once we do this, we actually have the Edison acting as a server host and having a Python script running in the background of the Edison. We can have the server connection sending the information back and forth.
Okay, so while sending data to the cloud is one of the more important aspects of our project, we also created an Android application, as you can see here. So our design approach was from a minimal standpoint. Some of the data that we explained include data such as the speed in miles per hour, as well as the battery life of the bike. And so we also have an odometer in our landscape view, and that displays data like the current trip history or the overall mileage of the bike. And so we also thought it was necessary to add a Google Maps widget because it's a bike, so we wanted to track the user's current location in real time. And so this updates in real time. And so we also added extra features to our app, to where if the user swipes left or right, you can either view the music player for a better user experience, or if you swipe left, you can view data such as graphs of the real-time data being pushed in through Bluetooth for a better data analysis.
Good morning, everyone. The system we've been using this semester is EMS. EMS stands for Edge Management System. It's a system brought to us by Wind River, where you can collect and manage data from compatible devices to raise your operational visibility and intelligence. With new information in hand, you can make better decisions and improve your business. Here are some benefits of EMS. It provides middleware software, solutions that securely connect devices and machines to the cloud, and efficiently collect and transfer machine and sensor data to a remote server. The remote server will then be used to perform data operations and analysis on the data received. Pre-integrated applications support machine data and readings into your systems and applications. Here's a diagram. Of how Wind River EMS works. As you can see, devices like embedded boards, such as Galileos or Edisons, are being connected to the cloud by EMS pre-integrated middleware. Before the machine cloud data is sent to the cloud, it goes through a gateway that points to a secure, scalable, and customizable on-demand infrastructure that will protect your network application and user data. Once on the cloud, you can remotely configure, monitor, and update your connected devices. There is one issue. Embedded boards that are connected to the cloud has to be stationary. But with our implementation of our phone application, the phone becomes the gateway, thus allowing the bike to be a device. Here's Camille with our implementation.
So essentially what we did was we turned the phone to act as the gateway, making the bike and the Edison as the device. And this creates an entirely mobile solution with seamless wireless connectivity between the bike, the phone, and the cloud. Oh, so the data items that we're sending to the cloud are the bike speed, the odometer, the battery levels, the trip distance, and the temperature. Monitoring these data values is useful for maintaining the longevity of the bike. So on EMS, we are able to view graphical representations of the data. So here we have an example of EMS receiving speed data in real time. So here the data is sent every second, and we can see the changes in the speed immediately. So not only can we see these data items in the cloud, we can also track our GPS location. So here we have a bike route from the engineering building all the way to the music building. And just as the other data items, the location is sent every second. And as it's received, a pin is dropped on the map along with its timestamp and coordinates.
So not only can the bike talk to the cloud can also talk back to the bike, and Aaron will talk about this.
We want to collect as much data as possible from the bike and sequence the status of the peripherals, which initially included the headlights and the horn. But we also added turn signals and remote start to the bike. In addition, this control walk pulls act as a bridge between the Edison and the Arduino Dash using a circuit communication. So as you can see here, the user will control, has user buttons act as inputs to the microcontroller, which are the headlights, horn, and turn signals. And through a switching circuit using the MOSFETs and relays, will control the peripherals, headlights, horn, turn signal, and also do a remote start. However, this remote start will be sent via command through the Intel Edison.
So in order to integrate our system, we have been modifying the code, the assembly code, which was building the data of the bike, and we have been at the zero UART communication to be able to get all of the data available to the phone, including the speed, odometer, battery level, and data travel. We can also receive the command from the phone via the board to start up the bike and get in the mode of the rider.
Implementing those three new PCB boards that our team just described to the existing structure of the bike and another challenge to our project. As you see, the bike structure, existing bike structure is very lean, with very little space available for new components. We use SolidWorks software to find this available space, and here in this you see two or three PCB boards cases located under the seat. In this location is the Edison board, and here is the peripheral PCB board.
So with this project, we feel we present a lot of value to our sponsors. So we think that the Wind River can sell this data that's collected to third-party groups interested in tracking their users. And we also created the world's first connected bicycle by leveraging a smartphone app and making the bike smart. And by connecting the bike to the cloud, we are able to do data analytics and allows for user remote diagnostic and monitoring.
So when it comes to the budget, we had a total of $2,000. We finished the project and we only spent like 69% of that, which is $1,371. The $629 left. As you can see from the pie chart here, we made two big purchases. The first big purchase goes towards the development boards, which includes the Intel Edison and SparkOne starter pack for the Intel Edison. Actually, we've ended up purchasing several Intel Edisons just to keep things going and to work simultaneously and to get the project done on time. The second big order goes toward the battery management system. We had actually several designs, and eventually we've ended up with a successful design that we talked about earlier. The rest of what we spend goes toward the accessories that includes the horn, LED signal lights, and some miscellaneous and spare parts.
Here's a timeline of our project over the course of this semester. On top are all the major milestones for the hardware team. One setback that we had was when we tried to change the existing code on the physical dashboard, we repeatedly burned out the microcontroller that's embedded in it. But eventually we overcame that by debugging the hardware and making sure there were no shorts around it. And because the dashboard was essential for us to develop our software and hardware around it.
And in terms of the software team, our milestones are on the bottom, and the main problem that we had was trying to connect to the cloud service. But once we got that up and running, we were able to send data from the bike to the phone into the cloud. So here's a little quick video of showing our bike mock-up connecting to the phone and to the Wind River website. So what you see on the left is our bike mock-up, and it's a motor that spins, and as it spins, the speed data is going to be updated real time on the phone. And as the phone is also updating, the website is also updating real time. So you can see the graph here updating. So yeah. So we would like to take this time to thank Neil from Wind River Systems, as well as Nate from both Motorbikes, as well as John Candy, Mark Bruno, and Dr. Kamala. And if you want any more details on our project and our progress, go to that site, dashboard.shu.edu. So with that, we are Team Dashboard, and thank you for listening.